December 7th, 1941, 0347 hours. Imperial Navy Communications Center, Pearl Harbor. The American radio equipment captured from the destroyed USS Arizona that morning contained technology that would fundamentally alter the balance of naval intelligence in the Pacific. The Japanese communications officers called it the Ghost Voice, a system that could intercept and decode their most secret transmissions in real time. The morning fog hung thick over Pearl Harbor as Commander Takeshi Yamamoto stepped into the captured American communications facility aboard the crippled USS Arizona. What he discovered in those first moments would haunt the Imperial Japanese Navy for the remainder of the war. Scattered across the radio room's metal tables lay equipment unlike anything Japanese engineers had encountered. Vacuum tubes smaller than rice grains, circuit boards with metallic pathways thinner than human hair, and most disturbing of all, a mechanical device that seemed to automatically decode encrypted messages without human intervention. Lieutenant Hiroshi Tanaka, the Navy's chief cryptographer, had been summoned from Tokyo specifically to examine this captured technology. As he powered up the American equipment using portable generators, the first transmission crackled through the speakers. What emerged was not static or garbled code, but clear Japanese voices, their own naval communications being broadcast back to them in perfect clarity. The Americans had not only been listening to every Japanese transmission for months, but their machines were automatically translating encrypted messages faster than human operators could decode them manually. The psychological impact was immediate and devastating. For 3 years, Japanese naval strategy had relied on the absolute security of their Type 97 encryption system, developed by the Navy's finest mathematicians and considered unbreakable by conventional methods. Every major operation, from the Pearl Harbor attack itself to planned submarine movements across the Pacific, had been coordinated using codes they believed were impenetrable. Now, facing this American communication technology, they realized their enemy had been reading their mail like an open newspaper. Captain Kenji Nakamura, commander of the Pacific Fleet's Intelligence Division, documented his first encounter with the captured equipment in a classified report that would later be discovered in Tokyo's naval archives. The American communication system operates with precision that defies comprehension, he wrote. Their equipment processes our encrypted transmissions and provides decoded text within minutes of interception. Most disturbing, their system appears to predict our operational patterns based on communication frequency analysis. The captured technology revealed capabilities that Japanese communications experts had thought impossible. The American system could simultaneously monitor hundreds of radio frequencies, automatically identify Japanese transmission patterns, and cross-reference decoded messages with previous intelligence to build comprehensive operational pictures. What the Japanese had assumed were random static bursts in American transmissions were actually encoded data streams containing real-time intelligence updates distributed across the Pacific Fleet. The true scope of Japan's communication disadvantage became clear during the weeks following Pearl Harbor as intelligence officers conducted systematic analysis of captured American equipment. What they discovered represented a technological gap so vast that it challenged fundamental assumptions about industrial capability and scientific advancement. The Americans had not simply improved existing radio technology, they had created an entirely new category of electronic warfare that made Japanese communication systems obsolete overnight. Traditional Japanese naval communications relied on skilled human operators, manually encoding and decoding messages using mechanical cipher machines. The Type 97 system, considered the pinnacle of Japanese cryptographic achievement, required trained operators working in teams to process even basic tactical communications. A typical encrypted message took 30 to 45 minutes to encode, transmit, receive, and decode, assuming perfect conditions and experienced personnel. Complex operational orders could require hours of processing time, creating dangerous delays in rapidly changing tactical situations. The captured American system operated on principles that Japanese engineers initially dismissed as impossible. Electronic circuits performed calculations that would require teams of mathematicians working for hours, completing the same operations in mere seconds. The American equipment could simultaneously process dozens of encrypted communication channels while maintaining perfect accuracy. Most remarkably, their system appeared to learn from each decoded message, becoming more efficient at breaking Japanese codes with each interception. Colonel Yoshio Nishimura, commanding the Imperial Army's Signals Intelligence Division, submitted a devastating assessment to Tokyo headquarters in January 1942. His report, discovered in captured documents after the war, revealed the mathematical impossibility of competing with American communication technology using conventional methods. The enemy processes our communications approximately 1,800 times faster than our best operators, Nishimoto wrote. They decode our most complex encryptions in the time required for our operators to transmit a single coded word. Japanese attempts to counter American communications superiority through traditional methods proved futile. Increasing encryption complexity only slowed Japanese operations while having minimal impact on American decoding capabilities. Changing code systems more frequently created confusion among Japanese units without significantly improving security. The Americans seemed to break new codes as quickly as they were implemented, suggesting capabilities beyond mere mathematical superiority. The psychological pressure on Japanese communication personnel became overwhelming as they realized every transmission potentially revealed operational secrets to the enemy. Radio operators reported increasing stress knowing their messages were being intercepted and decoded in real time. Unit commanders began avoiding radio communication entirely for critical operations, reverting to messenger systems that introduced fatal delays in coordinated operations. Intelligence analysis revealed that American communication technology represented years of scientific development and massive industrial investment. Their electronic components required manufacturing precision and material science advances that Japanese industry could not duplicate with existing capabilities. The Americans apparently solved fundamental problems in miniaturization, power consumption, and signal processing that Japanese scientists were only beginning to understand. By early 1942, Japanese naval leadership faced an unprecedented strategic dilemma. Their entire operational doctrine depended on communication security that no longer existed. Every major operation was potentially compromised before execution. The enemy possessed technological advantages that rendered traditional responses ineffective, creating what military analysts would later term asymmetric technological warfare. Conflicts where one side's technological superiority fundamentally altered the nature of combat itself. Faced with technological annihilation, Japanese military leadership initiated Operation Kitsune in March 1942, a desperate collaboration between naval intelligence, university mathematicians, and industrial engineers to develop countermeasures against American communication superiority. The project brought together Professor Ichiro Watanabe from Tokyo Imperial University's Mathematics Department, Captain Shiro Hayashi from Naval Intelligence, and engineer Kazuo Fujimoto from Mitsubishi's Experimental Electronics Division. The breakthrough came not from matching American technology directly, but from exploiting an unexpected weakness in electronic systems. Professor Watanabe's team discovered that American communication equipment, while incredibly sophisticated, relied on consistent power sources and specific frequency ranges to maintain optimal performance. Japanese scientists realized they could disrupt American communications without decoding them, a revolutionary approach that turned technological disadvantage into strategic opportunity. The solution emerged from studying captured American equipment under extreme conditions. When Japanese engineers subjected the devices to rapid frequency changes, electromagnetic interference, and power fluctuations, the sophisticated American systems became unstable, while simpler Japanese equipment continued functioning. This led to development of the Type J interference transmitter, designed specifically to exploit American technological complexity against itself. Captain Hayashi's intelligence division contributed crucial insights about American communication patterns observed during the Doolittle raid in April 1942. American forces relied heavily on centralized communication networks with real-time coordination between units. Disrupting these networks at critical moments could neutralize American tactical advantages, regardless of their technological superiority. The Japanese developed what they termed electronic lightning strikes, coordinated interference attacks timed to coincide with critical operational phases. Engineer Fujimoto solved the technical challenges of creating portable interference equipment that Japanese forces could deploy rapidly in combat situations. His design used readily available components to generate specific electromagnetic signatures that would overload American receivers and processing circuits. The equipment required minimal training to operate and could be manufactured using existing Japanese industrial capacity. The collaborative effort produced more than just technical solutions. It created an entirely new doctrine for electronic warfare that acknowledged technological inferiority while exploiting it strategically. Japanese forces would use communication silence and electromagnetic interference to create electronic shadows, where American technological advantages became liabilities rather than assets. Testing at the Yokosuka Naval Base in June 1942 demonstrated remarkable effectiveness against captured American equipment. The Japanese interference systems could render sophisticated American communication networks completely inoperable within a 15-mile radius. More importantly, the disruption appeared random to American operators, preventing them from developing immediate countermeasures. The project represented a fundamental shift in Japanese military thinking, from attempting to match American technological capabilities to systematically exploiting their dependencies. Professor Watanabe's final report to Naval Command concluded, "We cannot build better machines than the Americans, but we can make their machines work against them." Their technological sophistication becomes vulnerability when properly targeted. The first field tests of Japanese electromagnetic interference systems occurred during the Battle of the Coral Sea in May 1942, where Lieutenant Commander Akira Sato deployed experimental Type J transmitters aboard the carrier Shokaku. The results exceeded all expectations. American tactical communications experienced systematic failures during critical engagement phases, forcing their aircraft to operate without centralized coordination for the first time in the Pacific War. Captain Tetsuzo Iwamoto, commanding the Experimental Electronics Warfare Unit, documented unprecedented success rates during initial deployments. American fighter formations, typically coordinated through continuous radio communication, became fragmented when Japanese interference systems activated. Bombing runs that relied on real-time target updates from reconnaissance aircraft proceeded with outdated intelligence, significantly reducing accuracy. Most remarkably, American ships appeared to lose tactical awareness of Japanese positions during electromagnetic interference operations. Technical refinements emerged rapidly through combat experience. Japanese operators discovered that targeting specific frequency bands could selectively disrupt American coordination networks while preserving Japanese communications operating on different systems. Engineer Fujimoto's team developed frequency-agile transmitters that could rapidly shift interference patterns, preventing American forces from adapting their equipment quickly enough to maintain communications. The psychological impact on American forces became evident through intercepted communications during rare moments when Japanese interference systems were inactive. American radio operators reported equipment malfunctions, mysterious signal degradation, and communication blackouts that appeared to coincide with Japanese tactical movements. Crucially, American technical personnel attributed these problems to equipment failures rather than deliberate interference, allowing Japanese operations to continue undetected. Combat modifications improved system effectiveness beyond laboratory projections. Field operators learned to coordinate interference timing with traditional Japanese tactics, creating synchronized attacks where electromagnetic disruption preceded physical assault. The combination proved devastatingly effective. American forces lost tactical coordination precisely when Japanese forces achieved maximum concentration against specific targets. Manufacturing capabilities expanded rapidly as Japanese industry recognized the strategic importance of electromagnetic warfare systems. Mitsubishi, Kawasaki, and Hitachi collaborated to produce simplified interference transmitters suitable for deployment across the Pacific Fleet. Production reached 50 units per month by August 1942, with each system capable of disrupting American communications across tactical engagement ranges. Training programs developed at the Etajima Naval Academy created specialized electronic warfare officers capable of operating interference systems under combat conditions. These operators learned to identify American communication signatures, coordinate interference timing with fleet movements, and maintain equipment effectiveness despite battle damage. Their expertise became crucial as American forces began developing countermeasures. Advanced testing revealed unexpected secondary effects that enhanced Japanese tactical advantages. American radar systems, sharing similar electronic principles with communication equipment, experienced degraded performance during interference operations. This discovery led to integrated electronic warfare doctrine combining communication disruption with radar jamming for comprehensive denial of American technological advantages. By September 1942, Japanese electromagnetic warfare capabilities had evolved from desperate expedient to systematic tactical advantage. Combat reports documented consistent success in neutralizing American communication superiority during engagement phases, fundamentally altering the tactical balance in Pacific naval operations. The innovative solution had proven that technological sophistication could become a vulnerability when properly exploited. October 26, 1942, 0200 hours. The Battle of the Santa Cruz Islands became the decisive demonstration of Japanese electromagnetic warfare superiority when coordinated interference operations neutralized American fleet communications during the most critical naval engagement of the Pacific War. Commander Hiroshi Ozawa, directing the Electronic Warfare Squadron from the carrier Junyo, initiated systematic jamming that would fundamentally alter American tactical doctrine. The battle commenced with Japanese forces operating in complete radio silence, while American task forces maintained continuous communication networks coordinating movements across hundreds of square miles of ocean. At precisely 0630 hours, as American reconnaissance aircraft reported Japanese fleet positions, Ozawa activated coordinated interference systems across 12 Japanese vessels. The effect was immediate and catastrophic for American operations. Admiral William Halsey's flagship, USS Enterprise, lost contact with screening destroyers within minutes of interference activation. Fighter combat air patrols, dependent on continuous ground control intercept, became scattered across the operational area without tactical coordination. Bombing formations approaching Japanese carriers received contradictory targeting information as communication systems fluctuated between operational and disrupted states. Japanese combat reports documented systematic exploitation of American communication dependency during the 6-hour engagement. When American dive bombers approached the carrier Shokaku, electromagnetic interference prevented coordination between attacking aircraft and supporting fighters. Individual pilots, trained to operate within coordinated formations, became isolated and vulnerable to concentrated Japanese defensive fire. The psychological breakthrough occurred when American forces began avoiding radio communication entirely during critical phases, reverting to visual signals and predetermined tactics that negated their technological advantages. Japanese intercepted communications revealed American commanders attributing communication failures to equipment problems rather than enemy action, allowing Japanese electronic warfare operations to continue undetected. Captain Minoru Yamamoto, commanding the destroyer Akizuki, documented the complete reversal of tactical initiative during the battle's climax. American forces, denied their communication superiority, fought as we have been forced to fight, with individual initiative rather than coordinated superiority, his report noted. Their technological advantage became tactical disadvantage when electronic coordination failed. The engagement demonstrated that electromagnetic interference could neutralize American advantages without requiring superior technology. Japanese forces achieved tactical parity by denying American forces the communication networks that had made their sophisticated equipment decisive in previous battles. The Americans possessed superior individual components, but could not coordinate them effectively under interference conditions. Most significantly, the battle revealed American vulnerability to systematic electronic warfare that their doctrine had not anticipated. American forces had built tactical procedures assuming reliable communication networks, creating dependencies that Japanese interference could exploit. When communication systems failed, American tactical coordination collapsed despite maintaining superior numbers and firepower. Radio intercepts following the battle captured American confusion about communication failures that seemed to coincide perfectly with Japanese tactical movements. American technical teams, investigating equipment that functioned normally outside combat conditions, could not identify the source of systematic communication disruption during engagement phases. The Santa Cruz Islands engagement proved that innovative thinking could overcome technological disadvantage through strategic exploitation of enemy dependencies. Japanese electromagnetic warfare had achieved what conventional naval tactics could not: tactical superiority over American forces through systematic denial of their communication advantages. The electromagnetic warfare innovations developed by Japanese forces during 1942-1943 fundamentally transformed naval communication doctrine and established principles that influence military technology development to this day. The success of Operation Kitsune demonstrated that technological disadvantage could be converted into strategic advantage through innovative thinking and systematic exploitation of enemy dependencies. American forces, recognizing the effectiveness of Japanese electromagnetic warfare, initiated crash programs to develop communication systems resistant to electronic interference. The U.S. Navy's Project Brass, begun in early 1943, led to frequency-hopping radios, redundant communication networks, and electromagnetic hardening techniques that became standard for all military electronics. Japanese innovation had forced American technology development in directions that would define electronic warfare for decades. The broader implications extended beyond immediate tactical applications. Japanese electromagnetic warfare proved that sophisticated technology created vulnerabilities proportional to its complexity. This principle influenced post-war military doctrine, emphasizing system redundancy, electromagnetic compatibility, and resistance to electronic attack. Modern military communication systems still incorporate design principles developed in response to Japanese electromagnetic warfare innovations. International military academies study Japanese electromagnetic warfare operations as examples of asymmetric technological strategy. The principle of exploiting enemy technological sophistication rather than matching it became foundational to modern electronic warfare doctrine. Nations with limited technological resources learned they could achieve strategic effects by targeting enemy system dependencies rather than attempting technological parity. The human cost of innovation became apparent in post-war veteran interviews documented by military historians. Japanese electromagnetic warfare operators reported unique psychological pressures from conducting invisible combat that determined battle outcomes without direct physical engagement. American communication personnel described helplessness when sophisticated equipment failed during critical moments, creating lasting impact on military technology confidence. Industrial legacy proved equally significant, as Japanese electromagnetic warfare drove rapid advancement in electronics manufacturing techniques. The requirement for quickly produced, reliable interference equipment led to innovations in circuit design, component miniaturization, and field-deployable electronics that became standard for all military electronics. Modern electronics industry practices trace direct lineage to wartime electromagnetic warfare requirements. Strategic analysis, conducted decades later by the U.S. Naval War College, concluded that Japanese electromagnetic warfare represented one of the most significant technological innovations of the Pacific War. Their systematic exploitation of American communication dependency achieved strategic effects comparable to major technological breakthroughs while requiring minimal industrial resources. The innovation demonstrated that creative application of existing technology could be more decisive than raw technological superiority. Contemporary cybersecurity doctrine draws directly from Japanese electromagnetic warfare principles. Modern network security emphasizes the same vulnerabilities Japanese forces exploited: dependency on complex systems, central coordination requirements, and the difficulty of maintaining security when sophisticated systems become targets. The electronic battlefield of 1942 anticipated the cyber warfare challenges of the 21st century. The final lesson from Japanese electromagnetic warfare operations remains relevant to modern military strategy. Technological superiority alone cannot guarantee victory when opponents develop innovative methods of exploiting technological dependencies. The Japanese discovery that American communication sophistication could become a vulnerability demonstrates the enduring importance of creative thinking in overcoming apparent disadvantages. Today, electromagnetic warfare capabilities developed in response to Japanese innovations remain classified at the highest levels of military technology. The fundamental principle they established, that electronic systems are only as strong as their most vulnerable dependency, continues to shape military communication development and electronic warfare doctrine worldwide, proving that innovation born from necessity can achieve effects far beyond its original context.